Hello, Chemistry 30. Welcome back to doing a KB example. So this second example on the Ka-Kb sheet is a Kb example. It says a student dissolved 0.10 moles of potassium benzoate in enough water to make a 1.0 liter solution. What is the pH of the solution? So I first of all react my benzoate. I should have shown a dissociation, my apologies. I should show potassium benzoate dissolving to give me the benzoate ion and potassium ion. But I'm starting with my benzoate. I have my benzoate ion reacting with water to make hydroxide and my conjugate acid. So this is the base, that's its conjugate acid. I worked out my concentration, so 0.10 mole per liter divided by 1.0 liters equals 0.10 moles per liter. I set up my ice table. Here is my benzoate ion, hydroxide, and the the benzoic acid. So if you need a moment to do that, please do. All right, so moving on. Now, what's going to happen is we don't know how much this is going to ionize. It doesn't ionize a lot, so he starts with a concentration of 0.10. They each start with 0, so he's going to lose something. We don't know how much. They're going to gain the same amount because it's a 1-to-1 relationship. So we'll call that something x. So he'll lose x, and they will each gain x. So at equilibrium, he's 0.10 minus x. He's x, and he's x. Once again, if I put my Kb expression down, I will find out that I'm actually needing to use the quadratic. I don't want to use a quadratic, so what I'm going to do is I'm going to go ahead and try the assumption. Before I do that though, I need to get a Kb. The chart doesn't give me a Kb. So what I do know is that Kw equals Ka times Kb. So I can rearrange that to saying Kb equals Kw divided by Ka. Kw is 1.0 times 10 to the minus 14. The Ka is 6.3 times 10 to the minus 5. So now I can enter that into my calculator. And when I enter that into my calculator, I believe I get, again I can't do scientific notation it seems on this, so I'm using kind of longhand. You can check my numbers. 1.5873 times 10 to the minus 10. Okay? And again, I've kept extra digits. I could just call it 1.6 and keep the real number in my calculator, which I will do when I do my calculations. But this is the actual number that I got on my calculator, so I wrote that down. You can go ahead and write 1.6 because we have two significant digits, and our Kb is will be two significant digits because the Ka is, and the amount of water was. So therefore, we're going to end up with two sig digs. Now that I know my Kb, I can try the assumption. So 0.10 moles per liter divided by 1.5873 times 10 to the minus 10. I can tell you right now, that will be greater than 1,000. So now I can redefine my CEQ as 0.10 moles per liter. Okay, now we can actually begin our question. So I need to make a Kb expression. So if you need to pause the video so you can practice that, go right ahead. Okay, so I went ahead and made myself a Kb expression. So it's products over reactants. So it's a concentration of hydroxide raised to its coefficient of its exponent, which is 1, times the concentration of the benzoic acid, which is the conjugate acid for a benzoate, over the concentration of the benzoate ion. Now I take my ice table values for hydroxide and benzoic acid if I take my redefined CEQ for the benzoate. And I can write down my Kb. I'm going to just write it as 1.6 times 10 to the minus 10 here. And I have x and x. And that's all over 0.10. Okay, so now I've substituted my values in. Okay, so now what I need to do, the next thing, is do my algebra to get an x value. So I'll multiply both sides by 0.10. And that way the 0.10 gets out of the bottom. And I end up with x squared equals 1.6 times 10 to the minus 11. And then I'm going to square root that to get an x value. And let's see how well that works. So first of all, times 0.1. And then I'm going to square root. And I think that this actually looks like it's probably about right. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. So it looks like it's 3.984 times 10 to the minus 6. Okay, which is, again, more sig digs than I need. So I'm going to call this 4.0 times 10 to the minus 6, which is our hydroxide ion concentration. As you can see, hydroxide is an X value at equilibrium, and so the X value is the hydroxide ion concentration. Now, I'm going to need to make more board space. I'm going to erase things in a moment, so I'd recommend that you pause the video and make sure you've caught up and have everything down, because I do need to erase some things to make sure I have enough room to do my work. Okay, so if you guys pause, I'm just going to quickly erase. We erase the stuff on this side. Okay, welcome back. Okay, so now I have a hydroxide ion concentration. It asked me for pH. pH is related to hydronium. So I can do one of two things, and I'll show both things. You don't need to do both. First method is I'm going to go ahead and simply convert that to a hydronium. So I know the relationship Kw equals hydronium times hydroxide. And I can rearrange that to say hydronium equals to Kw divided by hydroxide. And I can get my hydronium. The other way to do it, so I'm going to set that up and do that in a moment. The other way is to take my hydronium and get a POH and then go 14 minus POH. So I'm going to do that. I'll do that maybe on top above here. So I'll just leave my hydronium there, erase my other work. Sorry for changing methods here. I can do this other one here while I have the number handy in my calculator. So POH equals negative log of the hydroxide ion concentration. So negative log of 4.0 times 10 to the minus 6 moles per liter, using the actual number in my calculator. And I can just do that right here. And I get 5.40 as my POH. Okay? If I continue with this one, I have a POH, not a pH. So I'm going to go 14 equals pH plus POH. So my pH will be equal to 14 minus POH. Equals 14 minus 5.40. And that will equal to 8.60. That would be one way to solve my question. The other way is to do what I started earlier. So Kw is hydronium times hydroxide. So hydronium is Kw divided by hydroxide. And so I have 1.0 times 10 to the minus 14 divided by 4.0 times 10 to the minus 6. Again, using the actual number that I had in my calculator from before. And if I go ahead and do that, give me a second here. So 0.0. So I get, looks like I get 2.51 times 10 to the minus 9. As my hydronium concentration. Oh, and that would be moles per liter. Okay, so now I can take that and put it into my pH calculation. pH equals negative log of the hydronium ion concentration. So negative log of 2.51 times 10 to the minus 9 moles per liter. And again, I kept an extra digit. I could have just called it 2.5. I shall just do that here. But in my calculator, I'm keeping the real number. So when I do that, I get 8.59998, which is 8.60, as we saw over there. So there's two different ways you could end this question. Once you have a hydroxide concentration through your Kb work, you can then go do the pOH directly from it, and then take the pOH, and knowing 14 equals pH plus pOH, get your pH. The other way is to convert it right away from hydroxide to hydronium. And here I got 2.5 times 10 to the minus 9 moles per liter. Then I put my pH formula down, and I also got 8.60. All right. Thank you very much for viewing, and we'll see you with the next video.